we started to look at areas under the curve, and we were looking at making rectangles under the curve, finding the areas of those rectangles, and summing them up, and that would give us an estimate. And the more rectangles we had, the better estimate we were going to get. And there were a couple ways that we could find the height of that rectangle. One was the left endpoint method. So that is where you would look at where the left value of your partition of one of your rectangles hit the graph. And so in this case, this would be your value when x was a, this would be f of a. That's the height of the rectangle. And then we saw that the base, and it's the case in each one of the rectangle, you would look at your end values of what you're bounding and finding the area between. In this case, it's a, b. And so you would look at the end value bound minus the start bound all over how many rectangles you want. And so let's just put it in. And we denoted that base of the rectangle by delta x. We could find the height by looking at the right endpoint of our rectangle, and you will find later today that that's actually usually the easiest one to do when we're setting this up into summations. And then the last one, you could find the midpoint between a partition, one rectangle, and that would be the height there, and that would give us that height of that rectangle so we could find the area. Okay, so we did a couple of examples of those. And now let's look at a couple of ways that we can use this with speed and with average values. So let's look at the following example. So we're looking at distance. So remember, distance can be viewed, or it can be viewed as the area under the velocity. And so let's explain why that's the case. So let's say that you're traveling 65 miles per hour constantly for, let's say, 5 hours. And so if we graph this where our y-axis was our speed and our x-axis was the time in hours, and if we wanted to find the distance traveled, because on here we have the speed, we have the time. If we wanted to find the distance traveled, let's say between the first hour and the third hour. Well, we know that distance, right, is equal to rate times time. So distance is equal to 65 miles per hour. And if we look at the time between 1 hour and 3 hours, that is 2 hours. And so if we multiply that out, we get that that is 130 miles. Okay, but notice that that's also the area that's under this constant rate between t equals 1 and 3. If we look at this, the height of this rectangle is 65, and this base of this rectangle is 2. So it's the same thing as this area under the curve. Okay, but that is where you're doing a constant speed at 65 miles per hour. But a lot of times we don't keep a constant speed, right? We're changing, we're slowing down, speeding up. So let's look at another example. And in this case, this example, we have a person who is running. So the speed in miles per hour of an Olympic sprinter was calculated at 5-second intervals for 45 seconds. The results are tabulated in the chart below. Okay, so for instance, at time 0, their speed was 0. At time 5, their speed was 17.2. Their speed is in miles per hour. etc. So it wants us to approximate the total distance in meters traveled by the sprinter from t equals 15 seconds to t equals 40 seconds by using either the left, well, we're going to do both, the left hand endpoint of each subinterval and the right hand endpoint of each subinterval. So we want to go through and we want to make a graph. And we want to make our graphs, and we can make our graphs so that maybe they're tick marks of 5. Time is going to go in our x-axis, and the speed is going to be our y-axis. Okay, so the first thing that they wanted us to do was they wanted us to look at the left-hand endpoint, and they wanted us to do this from 15 to 40. So what we would do is we would look at our table and plot our points. Sorry. So when t is, and it's our left-hand endpoint, so we're going to start our height of our rectangle at that speed at 15. So that speed at 15 is 20.1. And this distance in here is, or time is 5. Okay, we're going to have to be careful here though, and we're going to have to convert because this is miles per hour and this is seconds. And so we need to convert 5 seconds to hours. Well, there's 3,600 seconds in an hour. So 5 seconds is going to equal 5 over 3,600, which we can reduce. Okay, so you would do that for each piece. So in each piece here, we're going to have 5 over 3,600. So that's going to be the base of each rectangle, and the height is going to be that speed of the left endpoint. And so now we would go to 20. At 20, we have 20.4. We would go then to 25, and at 25, we have 20.7. We'd go to 30. At 30, we have 20.6. At 35, we have 20.5. And so we're going to find the area of each one of these rectangles, and we're going to sum them up. So if you do that, we're going to have, we can pull out the base because each of these have for the area the same base. So we can factor that out. So that 5 over 3,600 times the speed at that left end value for those 5 intervals. So if you sum that up, what's inside the parentheses and multiply by 5 over 3,600, you get that this is approximately 0.14208 miles that the sprinter ran. So you would want to do the same thing to find the right-hand value, but this time when you split up your graph, we're looking at the right-hand side. So again, at 15, the right-hand side is going to give us the height. So the first one is going to be at 20, and we get that's 20.4. The right-hand side of 25, oops, 25, that's the right-hand side, so it's the upper piece. So those are the heights of each of our rectangle. And again, that change in X, that base, because we want it in terms of hours, is 5 over 3,600. Okay, so we're going to sum the heights. So we're summing 20.4, that's the first one, 20.7, 20.6, 20.5, and the last height we're looking at is 20.2. So sum all those heights together and multiply it by our base, which I thought I had in here and I don't. And multiply that out. Okay, so we can find that distance again by estimating it by finding the area of each of the rectangles. And we find that that is approximately the base, which is 5 over 3,600, times the speed at the right-hand interval between 15 and 40. And if you sum up what's inside the parentheses and multiply by that 5,360, 5,306, sorry, 3,600, what am I thinking? Okay, I'm not, that's a problem. So this is approximately 0.1422 miles, which if we look at our answer before, very similar, 0.1428.